In this section, we're going to talk about planar graphs, which is where we want to try to draw the graph in the plane with vertices labeled as such and edges connecting vertices with the property that we do not want two edges to cross. To make this precise, a plane drawing of G consists of the following pieces of information. So first you have a function from the vertex set to R2 telling you where you're going to put the vertices as points. And then for every edge of your graph, you need a continuous function from the interval 0, 1 to R2 with the feature that f of 0 is u and f of 1 is v. So the whole point is that we're going to represent these curves for the edges as continuous functions. And this notion of continuous comes from topology, so I'm not going to give a rigorous definition in this course. For our purposes, the intuition is clear. You can draw the edge without lifting up your pen. And our one requirement is that given two edges of our graph, we're going to require that the drawn versions of the edges do not intersect, except possibly in the endpoints. So that means that for any point, if you're viewing these as functions over time and you're tracing out the edges, you don't want to ever have a moment in time where one of the edges crosses with another. And sometimes it's kind of hard to tell if a given graph has a plane drawing. For instance, consider the complete graph on 4 vertices. If you draw one of the Hamilton cycles as a 4 cycle, so you draw it as a square, you see that the edges have to cross. But if you move this vertex into the interior of this triangle, you get an actual plane drawing. So K4 does have a plane drawing. Similarly, if you take the complete graph or bipartite graph K23, you see in the standard way we draw it, it's not planar. But if I move one of the vertices in the set of size 2 to the other side, I do get a plane drawing of K23. Now, it seems hard, but you can try to look at K33 and try to do the same trick with one of the vertices. But then you still have 2 on one side and you still have crossings. So it seems hard to see if it's possible to draw K33 so that it has a plane drawing. And similarly with K5. So here you see that the trick we had before no longer works. You have a lot more crossings. As we will see, it turns out it's impossible to draw these two graphs in the plane without having a crossing. So we'll say that a graph G is planar if it has a plane drawing. As we'll see in the next video, there are ways to tell if a given graph is not planar. One of the first steps has to do with studying the concept of faces. So if you have a plane drawing of a graph G, and you remove the points that are in this drawing, so the vertices and the points along the edges, then what you have left has path-connected components called faces. And I labeled the faces here, so there's the face 2 here that's bounded by this trapezoid. There's this face 3 that's bounded by this other trapezoid. And then there's this face 1 that consists of everything outside the drawing. 1 is called the unbounded face here, by the way. So every plane drawing is going to have an unbounded face. And so in this case, there are 3 regions or faces. And throughout, we're going to let n prime denote the number of vertices in a plane graph. E prime is the number of edges, and f prime is the number of faces in a given plane drawing. Another concept we're going to need in a later lecture is the concept of the boundary of a face. So given a face in a plane drawing, the boundary consists of any vertex with the property that when you draw any disk centered at that vertex, the disk has to intersect your face in a non-empty intersection. So if I'm looking at region 1, then it turns out that every vertex of my graph is in fact in the boundary, because if I draw any circle centered at any of these vertices, you see that it has to have an intersection with the outer face. On the other hand, for edges, an edge is in the boundary if for any point along the edge, if you draw a circle at that point, it's going to intersect your face. So we see that for the boundary of face 1, we actually have every edge of our graph except this edge right here, because at this edge, if you take any point and you zoom in close enough, you can draw a circle that does not intersect the outer face at all. So that edge is not in the boundary. So one of the reasons to cover it so early is to make it clear that the boundary of a face is not necessarily a cycle. It can have leaf vertices and other kinds of weird things. And so for our first result, we're going to prove Euler's formula. What Euler showed is that if you have a planar graph G with a plane drawing, if your graph is connected, then the number of vertices minus the number of edges plus the number of faces in your plane drawing is always equal to 2. Euler actually proved this result for counting vertices, edges, and faces of a polyhedron, but for the purposes of this course, it turns out it generalizes to arbitrary plane drawings of a graph. So in particular, the number of faces of a plane drawing of a planar graph is always the same regardless of the actual drawing. And so for example, for our graph we've been looking at, there are 8 vertices, 9 edges, and 3 faces. And if you do the calculation, you should get 2. So let's prove Euler's formula using induction on the number of edges. In the base case, the minimum number of edges you can have is when you have a tree. So suppose G is a tree, then the number of edges is 1 less than the number of vertices. And every tree has a plane drawing, as so. And in this case, there's always only the outer face, so there's exactly 1 face. So then you have these 2 equalities, and if you do the correct calculation, you always get 2. So suppose your graph is not a tree, then it has to have a cycle. So take a cycle and take an edge on the cycle. Then if you remove that cycle from the graph, or delete that edge from the graph, you're going to get a smaller graph that also has a plane drawing. Just draw the same drawing as you did before, but don't draw that edge. The interior of this edge, E, that you deleted, has to lie in some face of the drawing of G minus E. So let's call that face F. Then you just look at what happens. F, once you draw the edge E back in, F gets cut into 2 faces. So what this tells us is that if we look at G take away E, it has the same number of vertices as G. The number of edges of G take away E differs from the number of edges of G by 1, but also the number of faces of G take away E differs from the number of faces of G by exactly 1. And this minus 1 and plus 1 end up canceling. And so this calculation is the same as the same formula when you take an edge away. And then by the induction hypothesis, this formula has to be exactly 2. And so the original formula is also 2. Note that this is a chapter where some of our proofs get a little less detailed, because if you notice, I didn't justify why adding this edge splits the region in 2, other than looking at a picture. That's because some of the finer details rely on topological arguments, which is beyond the scope of this course.